Welcome to this lecture. This is the fifth lecture of week 2. In this week, we have been discussing about product measures and their applications. We have also seen that we can also discuss the independence of random variables through product measures. This comes in consequence of the discussions that we are having in this week. Now, in this lecture, we are going to see an important application of these concepts once more. This goes back to this very basic question that given a probability law, which is some probability distribution on, let us say, real line, can you construct a random variable with that law? And the answer to this, as we know, is yes. But then suppose we are given multiple such probability distributions on the real line, can you construct random variables on the same probability space? So, that is the question we will try to answer in this lecture. So, without further delay, let us move on to the slides. So, as I have pointed out, we are going to talk about constructing several random variables, but on a single probability space. So, this will be the content that we will be focusing on in this lecture. So, let us start by looking at a very simple situation of two random variables. Suppose I am already been given two random variables x and y, but they are given on two different probability spaces omega 1 f1 p1 and omega 2 f2 p2. Now, as we have discussed in this week, we can talk about the product probability space on the Cartesian product of omega 1 cross omega 2 together with the product sigma field and the product measure. So, this gives us the new probability space. But now, we look at a relevant function that we define from the given functions x and y. So, we start by looking at this function x tilde. So, this is defined on the product space and it will take values in the real line, and it is defined in this way that for all points omega 1, omega 2, where omega 1 comes from capital omega 1 and omega 2 comes from capital omega 2, I assign the value as x of omega 1 in terms of the given function that we know about. Now, we are going to focus on the properties of this new function that we have just defined on the product space. The first thing that we are going to ask is whether this function is measurable or not. Now, to check the measurability, we will look at the pre-images of Borel sets under this mapping. Now, let us say capital A is some Borel subset of the real line, then x tilde inverse of A, the pre-image of A under the mapping x tilde is just defined in this way that we look for all points in the domain such that x tilde of those points lands up in the set capital A. So, that is just the definition. But now, as per the definition that we have taken for x tilde mapping, we have the value of this is exactly capital X of omega 1, and that is what should belong to the set capital A. But now, you observe that the condition that we now have does not involve omega 2, and therefore, what you have is that for all points coming from omega 1 satisfying this condition, and for all points coming from omega 2, if you pair them up, for all such points the condition gets satisfied, and therefore, the pre-image essentially is identified with this product type set, which is x inverse of A times the whole of omega 2. Once you have observed this, we follow the structure. This is a product type set. Moreover, since x is a given random variable, then the pre-image of all such Borel sets must be in the domain side sigma field F1, and therefore, this product type set that we have just obtained must be in the Cartesian product of the two sigma fields, and this Cartesian product of the two sigma fields, as we know, it is also contained in the product sigma field that we have constructed. Therefore, what we have obtained is that given any Borel subset capital A, if you look at the pre-image of that set under the mapping x tilde, that is in the product sigma field, and hence as a consequence we claim that x tilde must be a random variable on the product probability space, which we denote by omega fp. Similarly, if you define another mapping, let us call it y tilde on the product set, given by this formula, that for all points omega 1 comma omega 2, omega 1 coming from capital omega 1, omega 2 coming from capital omega 2, the value assigned is in terms of the given random variable y, and we assign the value y of omega 2. Now, we can again go through the similar computations by looking at pre-images under the mapping y tilde, and we can verify that y tilde must be another random variable on this product probability space. But now, we are interested in the link between x and x tilde and y tilde. So, let us see. Now, the first thing that we will highlight is the law of these random variables. So, the first thing is that x is defined on the probability space omega 1, f1 and p1. So, on top of this probability space, if you look at the random variable capital X, the law is given by p1 compose x inverse, and the new random variable that we have cooked up, that now has the probability law given by p compose x tilde inverse. So, we would like to compare these two probability measures. Note that these two probability measures both are defined on the real line together with the Borel sigma algebra. Now, take any such Borel subset of the real line and let us compare these two probability measures. So, the first thing that we should see is that under the law of the new random variable x tilde, we just have to look at the probability of the event that x tilde takes values in the set capital A. But then that is also written in the usual definition, that is probability of x tilde inverse of capital A. Now, we follow the definitions. The probability P is the product probability measure, and the pre-image as we have just computed has this product type structure given by x inverse of A cross omega 2. But since this is a product type set, as we have already seen, it is in the Cartesian product of the sigma fields, and hence as per the definition of product measure, we immediately see that it is P1 of x inverse of A and P2 of omega 2. But P2 is a probability measure on omega 2, and therefore, this value is 1, and therefore, we are just left with this expression. But now, we will simply say that this last expression is actually in terms of the law of the random variable capital X, and therefore, you have compared the two probability laws, and hence you claim that these two probability laws, both of which are defined on the real line, must be the same, and hence the conclusion is x and x tilde must have the same probability law, that is they are equal in law or equal in distribution. But note that both these random variables, even though they have the same probability law, they are in fact defined on different probability spaces. X is defined on omega 1 f1 p1 and x tilde is defined on the product probability space omega fp. Now, here what we see is that these two random variables, they are defined on different probability spaces, but they have the same law. Similarly, we can verify that y and y tilde, even though they are defined on different probability spaces, they are also equal in law or distribution. But now, what we have seen so far is that given two random variables x and y possibly on different probability spaces, we can construct new random variables x tilde and y tilde, both of which are now on the same probability space, the product probability space. Now, we will compare the relation between x tilde and y tilde. Let us see. So, we will choose any two arbitrary Borel sets A and B. Let us look at this event that x tilde takes the value in A and y tilde takes the value in B. Then let us follow the definitions. So, we will look for all points in the domain, which is the product space. Here we want to look at all such points such that x tilde of omega 1 omega 2 is in A and y tilde of omega 1 omega 2 is in B. Now, as per the definition of x tilde and y tilde, these values are nothing but x of omega 1 and y of omega 2 respectively, and therefore, what you have is that you can rewrite these conditions, essentially split up the variables, one in terms of omega 1 and another in terms of omega 2, and therefore, you end up having these product type sets, which are the pre-images of the set A under X and pre-images of the set B under the mapping Y. So, you have the product type set coming up here, but this was originally an event in terms of the new random variables x tilde and y tilde. But now let us look at the probability of this event. Now, as per the description that we have obtained, let us write the probability P in terms of the product structure, and the sets are also in the product type structure, and therefore, we follow the definition of the product measures. We end up having the product of these two probabilities. The first one is P1 of x inverse of A, the second one is P2 of y inverse of B. Now, let us rewrite in terms of the new random variables x tilde and y tilde. Remember, what we have said is that x has the same law as x tilde, and that is what we write first, and similarly y has the same law as y tilde, that is what we write here, and therefore, what we have just obtained is that for arbitrary sets A and B, which are Borel subsets of the real line, then the probability of this event is factored into individual probabilities, and hence what we claim is that the random variables x tilde and y tilde must be independent. So, let us summarize what we have obtained. So, what we obtain is that first we start with x and y, which are on possibly different probability spaces, but now we have constructed a new random variables which are x tilde and y tilde, but on the same probability space, which is the product probability space. Moreover, x tilde and y tilde are equal in law with the given ones x and y respectively. Moreover, x tilde and y tilde, which are now on the same probability space, can be compared. What we obtain is that they must be independent. So, using this procedure, what we can actually generalize further is that given n many random variables, finitely many, we can repeat this construction once more. So, suppose these random variables are defined on possibly different probability spaces omega 1 f1 p1, omega 2 f2 p2, and so on. Then construct the product probability space of all these probability spaces, and then you can also define the corresponding random variables which are denoted in terms of tildes, x1 tildes, x2 tildes, and so on. So, what we can actually construct is that all these new random variables must have the same law as the given random variables, and moreover these new random variables which are now on the same probability space, we can compare them and we find out that they are mutually independent. So, this follows by generalizing the construction that we have just obtained for two random variables, and we simply extend it to any finite number of random variables. But now let us take a further step backward. What we have done so far is that we were given random variables at hand, but now let us take one more step backward and let us discuss the situation starting with probability measures. Suppose we are given finitely many probability measures mu1 up to mu(n) on the real line. So, then we can construct individual random variables with these mu1, mu2, etc. as their law. Now, we can have these probability spaces which will be typically different. Now, these x1 up to xn are now possibly defined on different probability spaces, but has the law as the given probability measures mu1 up to mu(n). Now, we can follow the earlier construction starting with these random variables x1 up to xn and obtain these new random variables. And moreover, what we can actually obtain is that these new random variables can be defined on the same probability space, possibly on a product type probability space, but with the additional structure that these random variables turn out to be mutually independent. So, given certain finite number of probability measures, we can construct that many random variables on a single probability space that we choose, and all these random variables has these probability measures as their law. Moreover, these random variables must be mutually independent. Now, we look at a further consequence of this observation. We see that if we were given one single probability measure instead of multiple probability measures, let us consider the case of a single probability measures, but let us repeat the construction by repeating mu, the single probability measure, we repeat it. If we repeat it, then what we obtain is that we can construct a probability space omega fp, possibly a product type probability space, and moreover independent random variables on this probability space such that each of these random variables has the law mu. So, all of these are equal in law, but by our construction they must also be independent. So, hence what we have actually identified is that we can construct on a single probability space multiple random variables, finitely many, which are independent and identically distributed with the given law mu. Now, this structure of independent and identically distributed, this will reappear multiple times in our follow up lectures, and we shall abbreviate it as IID. So, all these random variables x1 up to xn that we can construct turn out to be IID, meaning they are independent and identically distributed with the same law. So, let us see, this construction that we just saw actually applies to a finite number of random variables. So, that is by our nature of construction that we are actually starting off with multiplication operations, which is a binary operation, and we just repeat it by the associativity property of the product measures that we have seen. So, if we repeat it finitely many times, we will see these finitely many random variables appearing with independence, structures and other properties. It is however possible to extend these constructions to countably infinite or much larger arbitrary collection of random variables, but with certain appropriate conditions. So, let us clarify this. So, we can justify this existence or the construction of IID sequences, for example, meaning this is countably infinite number of random variables with the same law. So, this kind of a construction can also be performed, but with a appropriate justification. Now, here what we have to additionally supply is some information about the joint probability distributions. Note that if you are dealing with a IID sequence of random variables, then for all finite dimensional distributions involving these random variables are simply product of the one dimensional marginal laws just by the independence. But if you are going to consider more general collection of sequences of random variables, then you can also still specify the laws of the individual random variables, and moreover you can also specify the joint distributions. Now, if you specify the joint distributions, they actually need to satisfy certain consistency criteria. This discussion involves some certain technical constructions on R infinity. So, if you are dealing with countable product of the real line, there if you want to construct these sigma fields and product probability measures, then it becomes a slightly complicated technical construction. So, here what you can actually do is that you can actually perform this construction. What we obtain is something called a cylinder sigma field, and we can justify the existence of some kind of a infinite product on this cylinder sigma field. However, we would like to point out that this cylinder sigma field has a slightly different properties than a typical finite dimensional Borel sigma field. So, we do not want to go into these technical details, but what we just want to point out is that all of this construction is following from this result due to Kolmogorov, which we call as the Kolmogorov's existence or consistency theorem. We do not want to get into all the details, but the main upshot of this construction that we will have is this following statement, that given a sequence of probability measures, let us call them mu n on the real line, we can construct a single probability space, let us call it omega fp, and a sequence of random variables on this probability space such that the laws of these random variables are this given sequence of probability measures, meaning the nth random variable has the law mu n. You can also additionally add certain joint distributional properties, but satisfying certain consistency criteria. Again, we do not want to get into the details. In what follows, we will just assume this fact that such a construction is possible, and we will be able to focus on certain properties of these sequences of random variables. Alright. So, with this understanding, let us focus on the modes of convergences for such sequences that we just constructed. So, in fact, what we have already discussed so far is that there are two modes of convergence that we have seen, namely The first one was the almost sure convergence of random variables, the second one was the convergence in LP. The LP convergence we also called it as the convergence in pth min. So, we have seen these two modes of convergence earlier, but with the understanding that we have obtained from this lecture about the existence of such sequences of random variables, we will just revisit this discussion in a much further detail about these modes of convergences. In fact, in the next week's lectures, we will introduce another new mode of convergence, and then we will see multiple examples involving these modes of convergence, and finally, we will also compare these modes of convergences which implies the other and what does not. So, let us move on and let us recall these definitions of the modes of convergences that we have already seen. In this lecture, we will just recall the convergence concept involving almost sure convergence, and in the later lectures we will further recall about the LP convergences and we will move on like that. So, let us recall the definition about this type of a almost sure convergence. So, as done earlier, we will see two different versions, one for measurable functions and second for random variables, and we shall use both of these concepts in our later discussions. So, let us recall this definition that for measurable functions, let us say Fn is a sequence of such measurable functions on a given measure space omega f mu. We say that this sequence converges almost everywhere to another measurable function which we denote by small f if you have a mu null set, let us denote by n. Mu null set simply means that it is a set in the sigma field such that its size under the measure mu is 0. So, take such a mu null set. So, then on the complement of that null set you can justify the pointwise convergence. So, as soon as you can construct or you can show the existence of a mu null set such that on the complement of the null set you have this pointwise convergence, then you say that this sequence of functions converge almost everywhere to the limit function small f. And here we shall use this notation to denote the almost everywhere convergence. Now, the similar definition we will just restate, but in terms of the random variables, and we actually call this convergence as convergence almost surely, or in short almost sure convergence. So, let us recall that definition once more. So, we will have a sequence of random variables, all of which are now defined on a single probability space, and we say that this sequence of random variable converges almost surely to a random variable x if there exists a p null set. Let us again denote it by n. So, here we mean n is some event with probability 0. If you have such an event such that on the complement of that event you have the pointwise convergence of this sequence of random variables to the limit function x, then we say that this sequence of random variables xn converges almost surely to the random variable x, and we shall denote it by this notation. So, we see some examples of this type of a convergence. Let us focus mostly on the measurable function situation. In later lectures we will specify and come back to examples involving random variables. So, let us start with a very simplified situation with the Lebesgue measure on the real line, and we look at this sequence of functions on this measure space. It is given by n times indicator of this interval which is open 0 to closed 1 over n. Here the n varies from 1, 2 and so on. So, for each n I now have a single measurable function, and that as soon as I vary the number n I get a sequence. Now, let us look at the pointwise convergence for this sequence of functions. So, first we fix a real number x less or equal to 0. Then for all such points you see that by definition fn of x is 0, since the point small x is not in the interval open 0 to closed 1 over n. Therefore, what you have is that fn of x must be 0 for all such small x, and in particular you can justify that by taking a limit as n goes to infinity you end up having 0 as the limit value. So, this appears whenever you choose the small x to be less or equal to 0. But what happens if x is positive? Then you note that for sufficiently large number n, you have 1 over n must be smaller than x, and hence again this point small x does not belong to the interval 0 to 1 over n, but this happens if your small n is sufficiently large. Therefore, for sufficiently large n, you again have pointwise values of the sequence of functions f n of x must be 0, and hence if you ignore the initial few values corresponding to n, after a stage n onwards you will have all the values are 0, and therefore, the limit must also be 0 again for positive values of x. Therefore, no matter what point small x you choose, the functions f n pointwise converges to the 0 function, which is the identically 0 function, and hence what we conclude is that we can take the set n to be the empty set, and here on the complement of the empty set, meaning the whole set, you have the almost everywhere convergence. So, let us make a minor change in this example and we will see how the almost everywhere convergence changes. So, we continue with the Lebesgue measure on the real line, but now what we do is that we look at this sequence of functions g n defined in this way, that we continue to take n as 1, 2, 3 and so on, but we look at this closed interval now instead of the open 0 and 1 over n closed. So, now we are looking at the closed interval 0 to 1 over n. So, now let us look at the values of these functions g n. Now, whenever x is not equal to 0, we can argue as before and show that the pointwise limit for these values of g n must again be 0. So, here just to repeat, if x is negative, then x does not belong to these intervals and then the function values is 0. If x is positive, you choose sufficiently large n such that again x does not fall inside the interval and therefore, the limit values is 0. But here something becomes different from the previous setting. If you take the point x to be 0 now, then what happens is that value of g n is n, and hence what you observe is that limit of g n of 0 when x equal to 0 turns out to be infinity. Now, we are discussing about convergence of real valued measurable functions, and we would like to discuss about the limit functions which are real valued only. So, here what we shall look at is this null set, which is the singleton set 0. Remember, the Lebesgue measure puts 0 mass on singleton sets and in particular on this singleton set. And therefore, if you now look at the complement of this null set n, which is the complement of 0, meaning this is the r minus 0 being the complement, for all such points you have the limit value being identically 0, and hence what you say is that we again have the limit to 0, but in the almost everywhere convergence setup. You see that here in this second example that we consider, the convergence does not occur for all points, meaning except for this point 0, everywhere else it occurs, but it does not occur for the point 0, and therefore, this is a nice example of almost everywhere convergence. In the next lecture, we shall see further examples and counter examples where the almost everywhere convergence fails, and we will also see examples involving almost sure convergence for random variables. We stop here. Thank you for listening.